The Bose-Einstein distribution represents the probability of a quantum state of energy E to be occupied by a boson. Bosons, again, are integer spin particles that do not satisfy the Pauli principle. Here is the probability of occupation of any boson with energy E. It ranges from 0 to 1, just like the Fermi case. The difference, actually a couple of differences. The most striking difference here is that there is a negative sign instead of a positive sign. That doesn't sound like much, but actually will play a very important role at low temperature. And here we do not use EF anymore because these are not fermions. We cannot use the Fermi energy. We use a generic letter mu to denote it. And this mu has an interesting name. It's called the chemical potential. Don't ask me where that name comes from. It's something we don't want to get it too far into here. But I can tell you one thing, that this mu is helpful in determining the total number of particles within our system. Okay? Given the total number of particles, I can fix that mu for you. And what if the number of particles is not even fixed? Well, you say, how can the number of particles not be fixed? You have this number of electrons, this number of protons, and so on, right? Well, in the case of electrons and protons, those traditional particles in the traditional sense, truly, indeed, the number of electrons or protons are fixed. You cannot change them. But when it comes to bosons, you can look at particles that are traditionally not thought of as particles, such as photons. Okay, photons. Photons really are the quanta of electromagnetic wave, right? And we can even talk about phonons. This is a new word for us, phonons. Photons are the quantum of electromagnetic waves. Phonons are the quanta of lattice vibration. The vibration of lattice particles in a piece of solid, each ion would, or each atom at the corner of the lattice would vibrate like this. The vibration is in the form of a wave. This wave is also quantized, just like electromagnetic waves are quantized. The quantum of electromagnetic waves are called photons. The quantum of lattice vibration is called phonons. This guy is for light, and this one is for sound. Okay, as the lattice vibrates, it can send a sound wave down the solid. So phonons are really associated with sound. Photons are associated with light. These guys, photons and phonons, their numbers are not conserved at all, are they? Photons can be created, destroyed, and phonons the same thing. If the lattice starts to vibrate, you have phonons generated, and if they stop vibrating, no phonons. Okay, so they're not traditional particles, and their numbers are not conserved. And it turns out when the numbers of the bosons are not conserved in a system, mu is equal to 0. We do not need that mu at all. Just to let you know, I'm not proving this. Okay, but it will be useful in our calculation later. Let's look at some famous examples of the Bose-Einstein distribution. First of all, what's called a phonon gas. So we have a chamber filled with, photon gas. We have a chamber filled with photons. Gee, you wonder what that is. It's basically filled with electromagnetic radiation. Okay, what is this? A black body, that's what it is. A black body has a chamber, remember, an empty chamber. You have a small hole where light can come in, radiation can come in. They're trapped inside. So inside the chamber, we have electromagnetic waves. Or we quantize them, we get photons, so we're talking about a photon gas. We can think of the black body radiation chamber as a photon gas. And we re-examine the Planck's radiation formula, black body radiation formula, with the in the new concept of photon gas. Photons are bosons because they have spin 1, which is an integer. And the Planck's radiation formula tells us the energy density per unit frequency spacing or per unit wavelength spacing. How much is the total energy of radiation within this chamber, whose frequency is between F and F plus dF? We looked at this example before, but now we're going to examine this from a brand new perspective. That is, we treat these electromagnetic radiations as a gas of photons. And between the frequency of F and F plus dF, first of all, how many photon states are there available? This is what we got before, using the idea of standing waves. So we just count how many possible standing waves are there. Each standing wave represents a photon mode, so it's a possible state. So this is what we got before. That was chapter 40. If you review chapter 40, you got this. dN equals 8 pi v c to the power 3 f squared df. That, again, is the number of photons whose number of photon states available. Okay, each state has a frequency between f and f plus df. Now, if you have a bunch of states available, will these states be occupied? Well, the answer is only partly occupied, and the occupation probability is this. Okay, if this probability equals 1, that's 100% occupied. If it's 0, then 0% occupied, and so on. So therefore, out of all these photon states between frequency f and f plus df, what is the total number of photons that actually can be found in these states? That will be the total number of available states multiplied by what? By the occupation probability, right? If there is an average of 60% occupation probability according to this formula, then only 60% of these states are filled with photons. So if you have 1,000 states, there will be only 600 photons to be found, because the occupation probability is only 60%. So you see, what we need to do is to find a product of Fe and Dn, this Dn. Dn, again, is the total number of photon states available between the frequency range, and Fe is the probability of occupancy of these photon states. So Fe times Dn is what? Is the actual number of photons that can be found with frequency of f and f plus df, right? Actual number of photons. And each of these photons have the same frequency f. Therefore, what is their energy? It's just h times f. It's just that simple. H times f. That's the photon energy. You multiply this and that. The number of photons times the energy of each photon. What do you get? You get a total amount of photon energy whose frequency is between f and f plus df. We call that du. Okay, so it's a product of three terms, Fe, Dn, and E. Fe is right here. Energy is hf, mu is equal to 0, because photons do not have conserved numbers. They can be created or destroyed depending on the energy of the system, so mu equals 0. And then you have this thing, which is right here, which is Dn, the total number of available photon states, times hf, which is E. Multiply these things to get three things together, and you get yourself this formula. This formula is one form of the Planck's radiation formula. Again, this is the total number of photon energy, total number of electromagnetic wave radiation energy per unit frequency. This is a form of the Planck's formula. We got it with much great ease due to our knowledge of the Bose-Einstein distribution. The second example I want to talk about when it comes to the application of the Bose-Einstein statistics is the example of phonons. In particular, we're going to examine the specific heat of solids at low temperature. We're talking about metallic solids. Okay, in a metallic solid, we have free electrons going around, and we already know how to find the contribution of the free electrons to the specific heat. But don't forget, we also have the positively charged lattice particles, right? You know, these are basically the metal atoms that lost 1 or 2 electrons, right? They're rigid, they're more or less rigid, but they can still vibrate. They can oscillate, and the oscillation is thermal in nature. So when the temperature is higher, they get greater and greater oscillation, which takes more and more energy. So that contributes to the specific heat. So basically, what I want to do now is to find the contribution of the lattice to the specific heat at low temperature. Why at low temperature? Because at high temperature, I know what the value is. At high temperature, we go to the classical limit. Okay, classical physics applies at high enough temperature. At really high temperature, how do we deal with all these lattice particles? Suppose we have 1 mole of lattice particles. The total number is Na. Each lattice particle is a 3-dimensional simple harmonic oscillator to a good approximation. Okay, in each of the 3 dimensions is a 1-dimensional simple harmonic oscillator. And when we write down the expression of energy of a simple harmonic oscillator in 1 dimension, we write 2 terms, k and u. K is 1/2 mv squared, and u is 1/2 kx squared. Each is a quadratic term, and therefore, according to the classical equipartition theorem, each quadratic term should contribute how much to the average value? Should have the average value 1/2 kt, right? Each quadratic term has an average value of 1/2 kt. So you add the kinetic plus potential term, what do you get? Twice of 1 half kT, which is kT, right? So each of these one-dimensional oscillator has an average energy of kT at temperature T. How many of these one-dimensional oscillators are there? There are 3 moles, because 1 mole of 3-dimensional oscillator each is equivalent to 3 one-dimensional oscillators in x, y, and z direction. So 3 Na, the total number of one-dimensional oscillators, times kT, the energy of each one-dimensional oscillator, that is the total energy of vibration of the lattice particles. CV by definition is dE total over dt. T is temperature, okay? And if you did that, you're just going to get 3 Na times K. Na times K is R, the universal gas constant, you get 3R. You get 3R. So classically, there is no temperature dependency here. You only get 3R for the specific heat due to the lattice vibration, and that's a constant down to absolute 0 temperature. Now, in reality, when we plot the when we measure CV as a function of T for these metallic solids, and we let the temperature go down, we find there is actually a drop. The temperature actually goes, as temperature goes down, the value of CV starts out at 3R, which is what we expect at high temperature, but it goes down, 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 and then goes down to 0. How does it go down to 0? Well, it's a complicated function, but at very low temperature, it's pretty much T to the power 3 here. T to the power 3. We're talking about, like 10, 20, 30 Kelvin-ish. Okay, but at ultra low temperature, we're talking about 1K or something like that. It is not T to the power 3 anymore, it becomes T to the power 1. We know where that T to the power 1 comes from, because that is due to the free electrons. So how come here is T to the power 3, here to the power 1? Well, T to the power 3 obviously is not from the electrons. The electron only contribute T to the power 1. So let's look at where T to the 3 come from. That's what the experiment tells us. So let's look at the theory. The first semi-successful attempt for us to understand the behavior of this CV as a function of temperature was the so-called Einstein model. The Einstein model describes a particular type of solid, imaginary solid, which is called Einstein solid. It was after the paper published by Einstein in the year 1907. So you see, Einstein was just really everywhere in modern physics, not just relativity. He was just everywhere. Einstein solid is a solid in which each lattice can only vibrate at one frequency only, and that frequency is called F0. So you wonder, what kind of solid only oscillate at one particular frequency? Well, the reason why Einstein made that assumption was to simplify the calculation. Okay, Einstein famously said that everything should be made as simple as possible, but not simpler. So he tried to get away with this. He says, okay, what if the frequencies are the same? What do I get? If it turns out to agree with the experiment, that's great. Otherwise, we have to modify this. So he started out with the simplest assumption on the frequency. He says, okay, basically we have, instead of a 3 Na number of classical one-dimensional oscillators, we have a bunch of quantum oscillators. The number is still the same, 3 times Na. 3 means 3 dimensions, and Na is the number of lattice particles. And each of them has this much energy, because the oscillation frequency is F0, therefore the energy associated with is H times F0. Okay, this is the number of phonon states available. Remember, each oscillation mode is called a phonon. Okay, each oscillation mode is, should be called a phonon state. But you have these states. Quantum state doesn't mean the state is necessarily occupied by somebody, right? What is the occupation probability? That is the Bose-Einstein statistics. This F represents the probability that a certain quantum state of energy E be occupied, and that energy is HF. And mu is equal to 0 one more time, because phonons do not have fixed numbers. E to the power energy over kT minus 1. That is the probability of each of these 3 Na states be occupied. So if you multiply N with F, what do you get? Here is the total number of states available. Here is the probability each state is occupied. So N times F is the total number of actual phonons that you can find with frequency F0, right? So total number of phonons per mole, that's that number, multiplied by the energy of each phonon, which is HF0. What is that? That is a total phonon energy within 1 mole of the substance, right? And that's that. So that's the expression for the total phonon energy, or energy of lattice vibration. CV is just the derivative of this function with respect to temperature. Now, the general derivative will get you a funny function, but let's look at 2 extremes, high temperature and low temperature. At high temperature, we should go back to classical physics. According to the correspondence principle, everything should go back to classical physics at high temperature. So at high temperature, let's see, HF0 over KT. T is very high. Therefore, you have e to the power of HF0 over KT. This number here on the shoulder of the exponential is quite small. We call it x. So e to the power x, when x is very close to 0, I can expand it as 1 plus x, right? So 1 plus x, then minus 1, so 1 is gone. So you just get HF0 over KT, which is x, in the denominator. The whole thing in the denominator replaced by HF0 over KT. HF0 cancels HF0, so the frequency doesn't matter. You flip it KT over, you get 3 NA KT. That's 3 RT. K times NA equals R. You see, we go back to classical physics, don't we? Classical physics says right here. Okay, CV, take the derivative, just get 3R, as expected. So that's one success story of the Einstein model. That is, it does give you the classical prediction of the CV value at high temperature. But of course, the interesting part is what happens at low temperature. So at low temperature, let's re-examine this expression for the energy before we differentiate it. KT is a lot less than HF0 this time. So you have a large power on the exponential. Therefore, in comparison, this 1, I can just ignore it, okay? Ignore it. So you take that exponential, flip that over, you get a negative sign. And that's what you get. That's what you get. So now you take a derivative. You have to take a derivative of the exponential function with respect to t, and that's what you get, right? That's what you get. Okay, now, remember, this is only true when t becomes very small. So let's say take t approaches 0. When t approaches 0, you have the denominator t squared, which actually approaches 0, which will tend to make this thing approach infinity. But you also have an exponential function on the numerator. And this exponential function as t approaches 0, you go into e to the power negative infinity, see that? Which also goes to 0. So you got 2 competing functions. They both approach 0. In the numerator, it is an exponential approach to 0. In the denominator, it's a power approach to 0. So guess which one wins? Of course, the exponential one wins, right? So overall, as t approaches 0, this expression approaches 0 because the numerator approaches 0 faster than the denominator. So we found that CV actually approaches 0 exponentially. Okay, it approaches 0 exponentially. Now, that is the second success story of the Einstein model. That is, we successfully predicted that at c approaches 0, CV should not stay at a constant 3R, rather should gradually approach 0. That's what Einstein model says. However, the Einstein model is inadequate in explaining the actual behavior when it goes to 0. It does go to 0, but it does not go to 0 as expected. As expected, would be good t to the power 3 according to experiment. This is not t to the power 3. It's some sort of exponential decay. So therefore, it's a correct trend going to 0, but it's a wrong function. It's not an exponential function. It's t to the power 3. So how do we get that t to the power 3? What was the key assumption that we made in the Einstein model? And that is, all the particles, all the phonons oscillate at a single frequency of f0, right? Now, is that a reasonable assumption? Not really, because you cannot restrict the frequency of these phonons. Some will oscillate at high frequency, some at low frequency, or even a range of frequencies. So this was an oversimplification, which led to this behavior which does not agree with the experiment. So let us relax this condition. Let us give the phonon a range of possible frequencies. Let's see how we can improve upon the Einstein model. And the corresponding model that improved upon the Einstein solid approach is a so-called Debye model. That was the year 1912. It was proposed by Peter Debye, who won a Nobel Prize for that work. And basically, there was a key improvement. It replaced a single frequency f naught, with a range of frequency between 0 and fd, d standing for dBi. How do we find this fd, the highest possible frequency of oscillation of these phonons? The idea is very simple. The total number of available phonon states is always 3A because we have 3 simple harmonic oscillators per lattice particle, and we have this many lattice particles, Avogadro's number. So every mole of lattice particles, there are 3A, that number of available phonon states. And now, these states have different frequencies, right? It ranges from 0 to fd. Between f and f plus df, how many states are there? Well, it's some constant times f squared df. Why f squared? It's the same idea behind how we get the f squared for photon gas for the electromagnetic oscillation of the black body chamber. It's the same idea. So af squared df. Okay, and a is a constant. I can find that constant by integrating this over 1/3 a fd to the power 3, and equate these two, and we get what a is. A is equal to 9na. N is Avogadro's number over fd to the power 3. So keep that in mind, okay? Keep that in mind. Now, what I want to do is something similar to what Einstein did. I want to find the total number, the total phonon energy of the entire solid. But this time, these phonons have different frequencies. So let's cut it down to frequency range. Between f and f plus df, what is the total phonon energy? Okay? What is the total phonon energy between this frequency range? Well, between this frequency range, I have only a limited number of phonon states, dn. That dn equals to a f squared df, just like here, a f squared df. Okay? Are all these phonon states occupied? No. This is the probability of occupation, Fe. This E is h times f. Phonons and photons, they're all oscillators. Therefore, the energy is also h times f for photons and for phonons. And each of these have energy of hf. So take dn multiplied by fe. What you get is the total number of available phonons within this frequency range times the energy of each phonon. Don't you then get the total energy of all these phonons within this frequency range? Okay, so you have to multiply these three things together. And then this is only the energy of phonons within this frequency range. What is the total energy of all the phonons whose oscillation frequencies are between 0 and fd? You have to integrate over dE total, right? And then that's what you get. Just integrate over this, you get this, right? Okay, you take the constants out, f to the power 3, and blah, 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 and so on. Now, you get this integral. This is not an easy integral to calculate. Right? It's not. However, let's take some shortcuts. There is a very important technique which we used that before once when we look at the Stefan Boltzmann law, and we'll use it again, and that is we introduce a dimensionless constant, dimensionless variable, I should say, dimensionless variable to replace f. F is not a dimensionless variable. hf over kt is a dimensionless variable because it's on the shoulder of the exponential. So let's define u as hf over kt. Replace df with du, and then you have to throw out this constant to balance it, okay? What is so nice about this integral? This is called the dBi integral, by the way. And this integral, whatever the value is only a dimensionless number. This whole thing is also dimensionless. The upper limit is also dimensionless. What you get, again, is a dimensionless number. It's just a number like pi or 2 or whatever. It's just a number. Okay. And you may not know how to calculate it. I mean, the way you calculate that is by expanding this function of 1 over e to the power u minus 1, this whole thing, in terms of an infinite series. Then each term in the series multiplied by u to the power 3, which also gives you the infinite series. And just integrate each term in infinite series and sum up the infinite series. After the integration, you will get your value. But that's not that important to us. We're not going to do that here, in fact. What we want to do is look at what happens at very high temperature and very low temperature. First of all, at very high temperature, that's the classical limit. Okay? In the classical limit, look at this upper limit of the dBi integral. hfd over kt. T is very large. So therefore, this upper limit is very small. U maximum, which is hfd over kt, is very small. T being a very large, very high temperature, much less than 1. So the integration goes from 0 to a very small number. Within that very small number, within that very small range of 0 to u maximum, e to the power u is almost equal to 1 plus u, because again, u cannot exceed that upper limit, which is very small. Okay, so replace e minus u, e to the power u minus 1 with u, because e to the power u is almost equal to 1 plus u. So the denominator drops only to u, so u to the power 3 over u, that's u to the power 2, right here. You can easily finish the integral now, and what you get is 3RT. After you plug in a value of a is right here. Plug the value of a. You get 3RT. Okay, so the lattice vibration has a total energy of 3RT as t approaches a very high value classical limit. You take the derivative, you get 3R. That's exactly what we get from classical physics. So both the Debye model and Einstein model give you the correct classical limit at high temperature. Of course, the interesting part is the low temperature limit, right? Let's see what happens when we approach low temperature. Will the Debye model give us the correct t to the power 3 behavior? So here's the quantum limit, or low temperature limit. This time, the upper limit of the integral, which is hfd over kt, is much greater than 1 because t is very small. Okay? It's so, t is so small that this number being very large, I can change it to infinity. Now you say, oh, what if it's not infinity? What if it's only 10,000 or whatever? You know what? If it's, as long as it's large enough, let's say 100 or more, you can change to infinity. Why? Because look at this integrand. This integrand, u is, as you approach, as u becomes large, let's say u equals 1,000, e to the power 1,000. Look at how big it is, okay, in the denominator. So this whole thing, the integrand approaches an extremely small value. Therefore, after, say, u equal to 1,000, you don't care anymore. You can take that 1,000 extend to infinity. You get very little difference in the integral because the integrand basically approaches 0. It doesn't matter whether you take that upper limit to 1,000 or to 1,000,000 or to infinity. Makes little difference. So might as well just take the upper limit to infinity, okay, at low temperature, which does not affect the integral. But now the integral is just a pure number which has no temperature dependency. Before, there was actually the upper limit dependent on the temperature, right? Now there is absolutely no temperature dependency. It's just a number. The Debye integral reduces to a pure number. Whatever it is, do I care about what it is? If I want to find the exact value of E total, I have to know this. But if I only want to know how CV depends on the temperature to whatever power, I don't care what that number is. Just a constant which I combine with A. See, that's the nice thing about making it dimensionless, because even if you cannot calculate the integral, after you make it dimensionless, all you're missing is just a dimensionless constant. You're not missing the important part, such as how it depends on t. So how it depends on t? Well, it's a constant, which you combine with this. The temperature dependency is t to the power 4. See that? That's the total energy. After you take a derivative, you get CV. CV is t to the power 3. That is the famous Debye's t to the power 3 law, which is valid at low temperature. That is in good agreement with experiment. Okay, so let's look at a plot of CV versus T for metallic solids. High temperature, classical limit 3R, and it goes down. This whole thing is called a Debye function, which can behave in a complicated manner depending on the value of the Debye integral, but at low T, it's a pretty good approximation to use t to the power 3. So that's t to the power 3 law. At ultra low T, we're talking about 1 Kelvin or less, we're looking at t to the power 1. Why is it true that the free electrons take over only at very, very low T? Because remember, the free electrons, they do not contribute much to the CV value, right? Because there's a ratio of T over TF, remember? Only a very small fraction of the electrons actually making a difference in thermal excitation. So generally, the free electron contribute a very small portion to the overall CV value. The dominant contribution is the lattice vibration, okay, lattice vibration. However, at very low T, the lattice part of the contribution goes down as t to the power 3, but the electron part only goes down as t to the power 1, no matter how much bigger this thing usually was. Now, at very, very low T, t to the power 3 cannot compete with t to the power 1. Okay, so t to the power 1 takes over, so this is the free electron part with a very small value A here. B is considerably greater, but at very, very low T, this term still wins over that term because of the power here. So this is the general expression of the behavior of CV at low temperature for metallic solids. Again, this term comes from the free electrons, which is only significant at ultra-low temperature. That term comes from the lattice vibrations, whose quantum are known as phonons. So this is another stunning example how the Bose-Einstein statistics valid for phonons, which is a boson, can help us understand the behavior of metallic solids at low temperature.